It is 6:30.
So this is if you come next week, come next Wednesday, you can unlock this potential.
Okay. All right. So, how is everybody going? How is everybody doing? My name's Jerry. I'm the president of the AI club, and we are just really a chill club. Really, things may sound intimidating at times, but I swear it's not. It's not something that we chase technical sake, because we also have more general meetings. So if you're interested in today's topic, you'd definitely be interested in next week's topic when we explain prompt engineering and some basic prompt engineering tasks you can use in your day-to-day tasks. But today we're going to kind of read through Attention is All You Need together. I kind of just want to. We seem to have a really diverse audience, which is great. But I do want to kind of understand where everybody's at in regarding to technical knowledge. So, who would say like they're pretty familiar with machine learning and linear algebra in general? One. Awesome. Okay. So that's what I kind of expected, which is great. We'll just have a more overview of this paper instead of diving into the detailed algorithms, which is still great. Anyway, so have anyone heard of the paper Attention is All You Need? Okay, a few. Have anybody heard about large language models? Right, I think that's most people. What about transformers? Okay. So basically, if you take any modern chatbot, ChatGPT, Copilot, Copilot is ChatGPT, ChatGPT, Gemini, Llama, Grok, the infamous Grok, Falcon. AlphaFold is not a language model, unfortunately.
Assets is a language.
No. No. Hi, Sujith. If you take any large language model, modern large language models, you will soon realize that it generates a bunch of text, and it uses a mechanism called attention in order to quote unquote machine understand the text and derive a word by word next token generation. So what that means is basically we have let's say a basic sets of words, right? So let's say if I want to here, I'm very new to this thing, so we'll see how that works. Actually, let me get an overview of the paper probably. That's fine. It's too old anyway. I have like a, I don't know, like 10 years old iPad Mini too. It's all good. It's totally fine. Anyway, so this paper is the start of everything. Came out in Europe back in 2017. Attention mechanism is what makes large language model work. So the proposal of this paper is a machine learning model architecture called the transformer. The transformer basically uses this mechanism called attention in order to derive a classification prediction model that generates a prediction of the next following word. Has everybody heard that, like the term saying like LM is an autoregressive model? Autoregressive, especially if you deal with longitudinal data, is a time series model that predicts the next outcome based on your past inputs. So it's very easy, right, to let's say generate called an autoregressive model on, let's say, stock data, right? I have the closing, the quarter, the opening, the mean, the whatever of a certain days of stock data, and from that data I can and the historical stock data of every single day, we can predict the next day. What is the next day's stock values going to be? So that's the autoregressive. But now, instead of predicting the next day of stock market, we're going to predict the next natural language word in a certain sentence or a certain paragraph, right? So basically, what attention mechanism tackles is this problem, and with this, back in 2017, it opened up a whole another possibility of modeling complex data like languages, right? Like as Will was mentioning, like amino acid sequences and amino acid trajectories. So this can be a lot, right? You're looking at this and you're like, what is going on? But basically, what you need to really focus on is kind of like just this right half, because when this paper kind of came out, this is nowhere close to what we have in our today's ChatGPT or later on Llama, Falcon, right, Alpaca models, language models, because this is a encoder decoder model. Does the word encoder ring a bell to everybody? I know encoder mean a lot of things, but in this context, it just means it will take some stuff, and then you will encode it into a representation, a latent space, a embedding of sorts, right? It's kind of funny because we call GPTs decoders, right? Oh, anybody know what GPT stands for?
Oh.
Some transformer.
Yeah, generative pre-trained transformers, right? So generative meaning it will generate the next words. Pre-trained meaning it's already been trained. So you just grab the model weights, the weights of the neural network instead of training it yourself. Transformers meaning this thing. And what really defines transformers is only really the attention. Of course, everything coming along with it, but because how different transformer architectures has been changed, the only thing that's common for transformer architectures is really just attention. Now there are also different kinds of attention, but that's just another can of worms. Hey Dion, grab a seat and grab a slice of pizza. So the left half is what our authors called a encoder model, and the right half is what models call the decoder model. The idea is that we are able to take an input of text, embed that into a series of ones and zero, so we can represent it in our computer, and then feed that text data into our transformer architecture in order to predict the next word in sequence. So I've talked so much, right? What is attention? Why is this paper called Attention is All You Need? This is by Google, by the way. Attention is the idea of you can represent a matrix of language or whatever tokens you want to embed, and then derive a relation or correlation or co-occurrence of every single token that you've ingested into your model. So let's say, I think this is where I swap out my little keyboard here. So let's say I have a bunch of text, right? So let's say I can say I love, and then on the left side, I'll see how well this works, right? And on the right side, I can have I love as well. So let's imagine that these are not, well, when we feed anything into a large language model, so let's say I feed in just two words, I love, right? I'm not gonna get exactly, I'm not putting in I, the letter I, and then entire word love directly into it. The first thing the model is not gonna do is actually called tokenization. So it will tokenize the sequence of text you're putting into it, and then you will take I as a single token and then love as a second token, right? So I want to space this out a little bit to make it look okay. Anyway, I thought there was a text is tough, but basically, what we're going to do is to imagine this I is not just one single one single text, one single token as a arbitrary data. This is going to be a high dimensional embedding that is represented as an array. Right? Array is a very common computer science concept where you basically have a list of values. Why the list? Because the list will allow us to capture multi-dimensional aspects, right, of any data or any concept. So let's say I have a row of data in my database. Let's say every row is a person, right? So let's say I develop a phone app. Let's say the app that got leaked. What was the dating app that got leaked? Yeah, the T app, right? Let's say the T app, right? So if you download the T app database, that was literally just a link, a click away on a link of a Firebase database. It's insane. It's literally an open internet bucket. So yeah, basically some guy, I don't know, maybe vibe coded an app, but didn't like securely store its database. So every user's like ID, their like location, their everything is just out on the open internet. Right? So that's what you get for trying to displace programmers with AI. And anyway, so if you look at every single user, right, what do you expect to see? Maybe names, maybe age, maybe date of birth, maybe locations, the longitude, latitude, right? We have a bunch of data there. And you can represent all of that data in a single list. And that is a single row of data. So what that represents is a user, right? Is the data that is associated with this user. So technically, theoretically, only this user can view her own data when she logged on with her own authentication. But of course, that was entirely available in the open internet. Anyway, but we don't want to represent users here. We want to represent each single semantic word. So we will have an array of values that represent I. We'll have an array of value that represents the word love. And that is what a token really is. It's a text embedding of each separate tokens. So what we can do with two same dimensional array is that we can calculate its inner product to get one single score. Now you may be confused because like what does that mean? Like user one or word one inner product word two. That seems counterproductive because now you're condensing a lot of data down. Well, the problem is that, right, we are trying to find the co-occurrence between two different tokens and represent that in one single word, one single data. So let's say I and I, because they're the same, I may have the value 0. Can I drag this? I dragged it. Nice. And then for sorry, let's say 1. And then for love and I, right, I may have an arbitrary value like 0.5, right? So if we take the embedding of I and multiply the embedding of love, we'll get an arbitrary value. And that's basically what this matrix multiplication is trying to do, is we're trying to derive a relation between each set of words and trying to represent that inside of our dot product attention mechanism. So here's where this very magical 3 letters come in: Q, K, and V, which represents query, key, and value, right? And the equations that is associated with query key value is attention equals to softmax of Q transpose times K times value. What Q, K, and V's are is they are 3 separate residual input that is that is calculated after we run through 3 different weights. So in neural networks, we have different sets of, just matrices as our weight matrix. What weight matrices means is just it's a linear combination of all the weights inside of each layer of our neural network. So basically, we want to calculate, we will train the 3 separate neural networks, weight of Q, weight of K, and weight of V, and we're trying to use our data to represent these tokens so we can get these scores and learn the underlying sequence that is in this whatever input that we have. Does that make sense so far? I mean, I can go a little bit more lower in abstraction.
Raise your hand if y'all have heard of a neural network.
Okay.
Okay, good amount. Well, yeah, this is our paper reading meeting, so this might be a little dense, especially that paper. That paper, I swear, I had to look it over like 5 or 6 times. So if you're not getting it, that's no worries. We all have been there. And
Yeah.
also the other meetings that aren't the paper readings are gonna be a lot more general.
Our next meeting is more applicable.
Yeah, our next meeting is actually prompting for any chatbot and how to get better results just by writing. So 0 coding experience required, 0 matrix multiplication.
0 math required.
Yeah, that's great. Yeah, over D of K actually. So basically, so we're training 3 different weights in our attention mechanism in order to derive a attention score for each of the sequence of data that we have. And that's the attention matrix. That's the attention mechanism. Now, a very intuitive thought is that if I have a very long sequence versus a very long sequence, how fast will my attention matrix scale? If you're a computer scientist, O of n squared, right? That's my runtime and my space complexity, meaning as my sequence length increases, as my amount of words increases, my attention mechanism will not double, not triple, but run quadratically, right? So x squared, x times n squared, n times n. And which is why large language models are very computationally difficult to train and to inference, right? Because not only because we have to use GPUs to handle the matrices and the tensors, we also need to deal with the quadratic scaling of our attention matrices. That's why NVIDIA's stock has been skyrocketing in the past few years. It has a lot to do with this equation right here. And in the analysis of linear algebra, we can derive that it's designed that Q has a size of n by d. K will have a size of K will have a size of n by d as well, and then V will then have will have a size of just n by k. So dimension of k. So what that means is that, right, when you multiply Q and T, the size of the Q times K. When you multiply Q by K, your size of your matrix will become n by n, and that matches with how we're modeling query and key here. So let's say this is query and this is key, and we're just going down this lower triangle in order to calculate our attention scores. Now, attention scores is just one part of the trick, right? Attention score only derives this correlation between each token. And then what you will do next is the scale basically divided by amount of matrices. So it's is scaled to a standard, so it doesn't just blow up because I have a longer sequence. And then we will do a final matrix multiplication on V, the third vector that we're so far ignoring, in order to get the total. Well, now it's no longer attention matrix. Matrix is now just the total representation of our text data. So what's next is basically essentially well, the original papers proposed a idea of an architecture that runs attention 3 times. That's usually not how this is implemented anymore, because we usually just have one multi-headed attention, but with multi-heads, multi-layers to represent. So you're not just running the attention matrix once, you're running that in each head to amount of layers that you have in order to derive the more underlying semantics correlance, and then you will do phi4, and that's just the training, the phi4 and back propagation. So that's just the loss function and how you train towards your ideal data. And then finally, you will reach a multi-layered perceptron. So just a very simple basic 2-layer, how many layer neural network in order to choose the next word. So if you want to train a large language model, what does the dimension of your multi-layer perceptron needs to be? Well, you need to have the choice of every single word in your English dictionary, right? If you're training an English model. If you are doing a multilingual model, then you need to add on whatever other vocabs is in there. So basically, it's choosing from a word bank. And then the multi-layer perceptron help you to find the right word in that word bank. Does that make sense? So let's say how many words is in the English language, like give or take, 30,000 maybe, more than that.
30,000?
I don't know.
Ooh, let me look.
Sorry,
I'm
maybe
looking
more
at
like
different data sets
yeah.
of that. I think the common ones you could probably get away with like 8,000, but in
Okay.
total, I think there's like 270,000, even including all the archaic ones.
I guess 300,000 make more sense, especially now your large language models is capable of generating emojis.
Yeah. Wow. And it can make custom emojis too now.
Really?
Yeah.
Oh, okay.
And obviously you would have to include names in that as well. Like proper nouns.
Yeah.
Once you get the proper nouns, that explodes the data
And
system.
then if someone else invents something, then like you have to use that language they invented it.
Yeah, but usually that's handled by tokenization. So there are basically 2 ways of tokenization, right? So let's say for the term embedding, right? I can encode it into embed, and then d, and then ing. I think that's actually the earliest form of embeddings for like GPT-2. I think they're not doing that anymore. So the whole word is like the whole embedding. The benefit of like separating out the prefix, the postfix, and then the root is that you'll have a little bit less because you can just build the word together, but at the same time there's a lot more for the model to learn instead of just learning like the meaning of the whole word. But yeah, basically let's run through some of the more illustrative let's say examples. So let's say I do something like I love. So what this is a great website, by the way. It's called Transformer Explainer. It's a visualized sequence of how query key value runs into your attention mechanism, runs into every single head, and then finally runs into your multi-layer perceptron and give you a probability distribution of what word it should be next. So let's run through some of examples. Let's say I love, right? As I did earlier. So what we are going to have is that the model will ingest the tokens I and love, right? And then it will run through the 3 weights of attention that I mentioned. The weight of query, the weight of key, and then the weight of value. So after running to all three neural networks, we will run into the attention mechanism with the function of softmax qk over d times v. And now we see that we have actually 12 heads, so it's basically the same mechanisms, but it may have like different values depending on which head we're in, and that's just more weights that we're training here to capture more of the semantic richness. And then for the transformer block, we may do that again, and again in order to repeatedly capture some of the underlying semantic richness. So you can see, let's say the correlation between I and I is 1. Maybe I to love is 0.98, and then love to love is 0.02. But anyway, then what we can do next is run through a multi-layer perceptron based on the attention value in order to derive a classification of what the next word will be. So the large language model thinks the next word with the greatest probability should be the, and this is the top 5. This is the top 5 next word that is probable to this model right here. So let's say I love pizza. Well, again, according to the probability, it's probably gonna do like I love thee, or I love you, or I love it, or I love this. But let's say I love pizza. What's going to happen is that we will run through another QK view again and add on to this attention matrix, right? So can I keep doing this? Yes. So I can do that again and again and again and just keep expanding my attention matrix, right? And then into my output and run through my NLP, it will keep trying to predict the next word. This is a very small, no, actually, I think I just didn't give it enough time to run. What do we want to generate? Let's try a different example.
Let's see.
I'm gonna do Elon Musk.
Can you ask it a question? Or do you
No, this is too small of a model to do
start
it.
of a sentence. So give it the start of a sentence, and then it's going to predict the next word in that sentence. So
Elon Musk hates. We'll see.
what's a classic quote?
Hates it. Yeah, that's kind of.
Copy
It's
the first 10 lines of the Constitution.
yeah. Actually, what is the first 10 line of
I'm not
"We the people"?
True.
We the people. Actually, if I just do "we the," it's probably gonna give me people. Let's see. See, we the people, right? So it does it does do with the people. Okay, it turned to fans because there is a temperature matrix to give a probability to generate the less possible word. So the probability for fans is only 5.9, right? But then the probability for people is 78.94. So 78.94 of the time is going to generate people unless I turn the temperature way down, right? So exactly, it learned the term "we the people," right, with a lot of confidence. So what this does, right, again, is just choosing from the entire word bank of the English language, but giving the most probable result that may be the next word, which in this case, "we the people," right? So that's attention mechanism, and that's what kind of the model does. And somebody asked about a question, like asking it a question. Yeah, so every model that you first train, it never answers questions. Like every model that, like large language models you train, like first time you train it, after all of the text data, as you have heard, like maybe like Discord data, Common Crawl, Wikipedia, whatever text data is trained on, it will never answer questions off the bat because it doesn't know like how to like question answer works, right? It just try to predict the next word. So we the is gonna predict people because it's being trained on the Constitution. However, the way you make a model question answering capable is through reinforced learning through human feedbacks. So basically what you're going to do is basically use reinforced learning to allow it to kind of traverse the field of its own like possibility of answering, but you will punish it until it's starting to like reply to you. And once you train that, then the model becomes like, hi, I'm an assistant of, I'm a chatbot. How can I help you today?
Yeah, I found a good question to like visualize this, or a good statement. If you start that with the worst movie of all time is the movie, and then start with a little double quotation, you'll see like just how few options it has.
I'll give it a regular temperature and wait, what?
Yeah, look how many 0% there are.
Hold on. Let me. I don't know why I had people in there. Let me regenerate this. It's the if. Oh God. Okay, so there's star and there's S is F B I C and
And
D,
all of those are 0%.
Yeah, I mean, if you turn up the temperature a little bit, okay, that's top K. That may like go up a little bit, but that's super high temperature. 0.8, yeah. I mean, it's around 2% for each of these. But maybe but again, right? If earlier on you didn't just ask the worst movie of all time is. You may have talked to your chatbot about a little bit about Star Wars. You may say like, I like Star Wars, but I don't like Star Trek, for some stupid reason. You may say, and then you ask the worst movie of all time is the movie. It's probably gonna say Star Trek because it based on its previous text, right? It kind of associated Star Trek with like something that you don't really like, and then in that context, it's going to probably associate worst with Star Trek, and then generate the worst movie of all time is the movie Star Trek. But that's kind of where a lot of researchers are saying like, oh, LLMs just want to make you happy, and that's probably why, right? Because your attention mechanism essentially determines that certain words is going to have a high correlation with certain words, and then that's part of that. It's part of the core mechanism that makes it do so, right? But that's the basic. So now you really know how a LLM work. What I think is also interesting is that the attention is all you need really isn't as blockbuster as most people think. I think it's just only because Google kind of is the only one that really revenued on that at first. Of course, Google at first, and the reason they did an encoder decoder, encoder decoder model is because they try to do translation, right? They try to use that model probably for Google Translate or other products. And of course, Google kind of went that way of embedding words. So let's say Google BERT, bidirectional encoding transformer. The purpose of that is to just return you the embedding and not to generate the next word. But OpenAI is ultimately the first company really to develop a good chatbot that led them to launch GPT-3 eventually. But my point with talking about attention is that all of a sudden, is that attention isn't the only. This attention is all you need is not the only paper that talk about attention even in the same journal. In the same class of 2017 Europes, where attention is all you need is published, there are 10 other papers on attention. and of course, it's not gonna be the same implementation of what attention is, because back then attention is more of a general idea of correlates between each word, but at least attention is all you need is the first one that made attention mechanism into its own neural network architecture called transformer, right? And even for a paper deep set, it's a more, this one is AWS and Carnegie Mellon. It's more on the set theory kind of representation of data, but it still have a very similar implementation like attention, where it gathers the correlates just like attention, and then calculate its possibility of distribution of the next sequence. So even like right here, right, given alpha and mo predict theta. That's the very broad quick overview of some similar ideas that is also being proposed. So if attention is all you need isn't published, I would say the progress of human developing an LM was right on the edge back in 2017, just because we were going that way, and a lot of the research were trying to, again, right, hash embeddings for efficient word representations. I just saw that. That's funny. Of course, I haven't read everything yet. But right, that's kind of what Google's BERT is doing after they've done attention is all you need. But they use hash functions, and then they import hash vectors. Okay. I don't think that's close to attention though, but they do compress the embedding size. Anyway, so yeah, that's the world of attention is all you need, and the sad reality of academia right now is basically you have to quote attention is all you need every time you pump out a new AI paper, because you can't really say, oh, this research is the or whatever other research like deep sets or other paper that had attention in its name is my source of inspiration and the related work to my research. But credit to the Google guys, transformer architecture is one of the most used neural network architectures as used in protein prediction as well, right? Amino acid sequence prediction, as well as now it's also used in image generation and image embedding. Because instead of using stable diffusion like they used to, you just slap a image embedding in your LMs, and your LMs can generate image, and it's actually not too bad. But yeah, this is just the overview. I think I'll bore you guys too much if I go into the math, but a basic overview of what attention is. Any questions? Any comments? Any
Concerns?
maybe.
Hopefully no concerns.
Okay, hopefully.
Nice job, Trinity.
Thanks.
Yeah, how many pages is it? 15.
Something like that.
15.
It's not a very well written paper per se. I mean, at least you have some cool looking graphs. This is you can put it as a sticker on your back of the.
The what's it called? If you go all the way down, they got the little appendix visual. That's kind of nice after the references. Oh.
Not on Europe's archive.
Yeah.
Oh. So you need archive.
Jerry, how's the paper going?
Which one?
The word Dr. Fal.
I don't know. I mean, they've submitted it, so hopefully you get approved and published.
There we go.
Oh, right. I forgot they have that on archive. Yeah. This is a little bit, it looks a little bit different, right, than the attention matrix, but it's the same thing. So for the word making, you can think about this like the same attention square, right? The attention matrix, but this is just taking one role and then kind of finding the correlation between this single word with all the other words. So let's say making have a high correlation over multi-heads, have a high correlation with more difficult, or making itself, right? Or 2019. I want to. So this will look like if you visualize every single one of them. I want to find the more important ones. Ah, yes, it's right. So let's say this string of text is like the law will never be perfect, but its application should be just like whatever that else says. So when the text says it, what is it? Right? That's like the age-old questions about natural language processing and semantic representation. What is it? What is it's referring to? So then in this case, the LLMs will have a higher attention score with law. So it thinks it is more representation, or represents the law more than application, right? So and it will make sense, right? The law will never be perfect. It's still talking about the law. We've not changed the subject here, right? So this is why attention mechanism is useful of generating the next word or just semantic representation, because it can find the correlation where the representation of data is close, right?
So, and they said it there. That is an example of anaphora resolution, where it uses previous knowledge to figure out what a pronoun is currently. So it's, they're like, what is it's? Oh, the law is what it is.
Yeah. Exactly. Yes.
Yeah, so I love this stuff. It's all very complex, right? All to be able to help us like make better content and stuff through like ChatGPT and all that. There's a lot of money going into this stuff though, and just from industry myself, it's like we only can make so many emails with ChatGPT and like search so many things.
Yeah.
What do you see as like the real impact for spending so much time and effort on this amazing technology? Not like high level like humankind, but even just like the small business standpoint. Or do you have any ideas in your head from your own research of like how this stuff could help us more than just like chatbots?
Well, that's a great question, right? Because everybody, when people talk about AI nowadays, what do you think of? ChatGPT, right? It's like, okay, I mean, there's so many other things in AI, right? There's so many other wonderful technologies and algorithms that are very intelligent, like machine intelligent, right? But we just don't really consider them. But, well, outside of chatbot, I would say, let's say, a lot of it will be used in semantic search, and that's already implemented, right? That's what RAG is. It's a semantic search of your current existing data set, but instead of searching by terms and word, you're searching by the correlation of embedding. So let's say if you search it, and then within this sequence, you will get law, right? But instead of each word, you can be each document, right? So that's what basically how Google search now. Is basically it has a semantic embedding of each, let's say, website or title of the website or the entire web page, and then whatever you search in the search bar will find the closest co-occurrence of whatever document and web page it will link you to, right? So that's, of course, search engine is big. There's also, and in my own research, I'm just more interested in like capturing underlying semantics for prediction algorithms. So let's say predict someone with a certain personality disorder or personality like trait, right? That's still being improved and proven to, if that's probable, that's most of it, and of course we don't see much of that being on revenue like right off the bat, right? So of course, I mean, we're barely revenue, like the industry is barely getting revenue off of chatbot alone. I mean, ChatGPT may like charge you $20, but it's still free most of the time when you just want to ask it a simple question. And Sora is trying to like charge like $5 to generate videos. So I don't know. I don't see a way to just like develop a whatever and make money because it's like the best businesses are coming from pain points, right? So I have this pain point, and then let me tackle this pain point. If you come up with a solution and sell that solution, you may not find the right problem to sell that solution to. So I think that's the fundamental like quote unquote issue with like just hyping up the AIs, because what are you trying to sell to? What solution is this for? Who is it for, right?
Yeah.
What are you trying to solve? And of course, some people will pick up and say, "Hey, this is great. I love doing this with ChatGPT or whatever." But then, end of the day, you're still not tackling a pain point, and that's probably why 90% of the AI startups fail, according to like
Yeah.
one I think what MIT study.
Or just any business.
Yes,
Got it.
exactly.
Is there a
Yeah.
particular like thing you're looking for?
So my fund right now, my boss was like, "Hey, I want more synthetic data for us to model for some of our investments." So he almost wants to create a sandbox of like the market,
Hmm.
and he was like, "Hey, I want like some data." So he read something on Gartner about some other funds who are playing with like future data that hasn't happened yet in the market.
Okay.
Like simulations?
Yeah, so we play with past data to build models on forecast cash flow of some of our opportunities. And we focus on, we're pretty agnostic, but we focus mainly on like energy, defense, some security, and then SaaS in general. So if you vertical, if you have any SaaS out there, we'll look at the IP for it. But he does want to, they hired 2 quant guys, so they do